Here we see again our recipe for calculating Haar measure. And in order to prove left invariance, we used this translation here of a coordinate system on the Lie group. And now let's see what happens when we want to study right invariance in the same way. So we just move the h to the other side. And now we calculate the Haar measure again in terms of this parametrization here. What do we have to do? We write g tilde of x inverse dg tilde of xj, dg tilde dxj of x. And now this is g of x times h inverse dg dxj of x times h. And this time the h's don't go away because they are on the outside. So we get g of x dg dxj of x in the middle and h inverse and h on the outside. But this here we recognize from above, that's just this. So we can recover these coefficients a, k, j here again. But the whole thing is conjugated with these h's. So now we get h inverse, and here we write I times sum over k, xk, the algebra basis, akj of x, and then the h from outside. So we replace this by this. Now, what happens when we conjugate a Lie algebra element with a group element? That's actually again a Lie algebra element. Because if you think for a moment, you have a curve in your group, let's say that goes through the identity at 0, and by taking the derivative we get a Lie algebra element. If we conjugate this with the group element, then the thing still goes through the identity at 0, and we take the derivative at 0, and then we get just the pink stuff here, the Lie algebra element conjugated. So we can really here write this as, let's say, I times sum over k and l. Let's say xl phi lk of h ak j of x. Blah. So the pink thing is now the sum over L, and the x's and some coefficients here that depend on the h. Yeah? H inverse xh can be expanded in the Lie algebra basis again. And from this we now read off what d mu at g tilde, d mu at gh looks like. Because here we have just a matrix product. So this is, if we expand here directly, we could also write this is I times sum over L, xl, and then let's say a tilde lj of x. So this is now, this a tilde is now the product of this matrix phi and the matrix A. We now get d mu of gh is determinant of this matrix phi times the determinant A dnx because that's our determinant of A tilde. And now that's not the same as d mu of G, which we have here. There's this additional factor here, this determinant of the phi of H. And if this is 1 for all group elements H, then we call the group unimodular, and the thing here we call the modular function. And in that case, the left invariant measure is also a right invariant measure.